There are four different criteria based on which the superconductors can be classified. This includes by their response to a magnetic field. That is the first criteria. Second one is by the theory used to explain superconductivity. Third one is based on their critical temperature. And fourth one is based on the material used. Let us consider the first criterion, that is based on the response of superconductors to an externally applied magnetic field. Depending on this, superconductors are classified into two categories: type 1 superconductors and type 2 superconductors. Type 1 superconductors have a single critical magnetic field value above which all superconductivity is lost. That is, the material becomes a normal conductor above the single critical magnetic field value. Type 2 superconductors have two critical magnetic fields between which they allow a partial penetration of the magnetic field. Thus, the type 2 superconductors show three different possible states of existence, namely a superconducting state, a mixed state, and a normal state, as the strength of the externally applied magnetic field increases gradually. The second criterion of classification of superconductors is based on the theory that can be used to explain superconductivity. The most valid theory used to explain superconductivity is BCS theory of superconductivity. Those superconductors for which BCS theory and its derivatives can be used to explain superconductivity are known as conventional superconductors, whereas the same theory cannot be used to explain the phenomenon of superconductivity exhibited by unconventional superconductors. The third criterion of classification of superconductors is based on the critical temperature at which a normal conductor makes a transition to the superconducting state. We all know that liquid nitrogen is a colorless, odorless gas which can act as a coolant, and it can be used to lower the temperature of a specimen by keeping the specimen in contact with it. Liquid nitrogen's efficiency as a coolant is limited by the fact that it boils immediately on contact with a warmer object, enveloping the object in insulating nitrogen gas. There exists a category of superconductors which reach their superconducting state by just cooling them with liquid nitrogen. This means that their critical temperature is greater than 77 Kelvin, that is Tc is greater than 77 Kelvin, as the boiling point of liquid nitrogen is 77 Kelvin. On the other hand, there exists another category of superconductors which cannot achieve superconductivity just by cooling it with liquid nitrogen, as their critical temperature is below 77 Kelvin. Such superconductors are known as low temperature superconductors. And to convert those specimens to superconductors, we need to use techniques other than cooling it with liquid nitrogen. These methods include mixing, calcination, sintering, etc. Low temperature superconductors refers to niobium based alloys and niobium tin and niobium aluminum superconductors that were already in use prior to the discovery of high temperature copper oxide superconductors. Niobium titanium and niobium tin are often termed as technical superconductors because more than 95% of all superconducting magnets have been made with them. They typically require cooling to 4.2 Kelvin, where liquid helium is the most common coolant, and in some instances to below 2 Kelvin, where we use superfluid liquid helium as the coolant. The fourth criterion for classification of superconductors is based on the type of material used. Some superconductors are pure elements such as lead or mercury, but not all pure elements behave as superconductors, as some never reach the superconducting phase. These are known as chemical superconductors. That means superconductors made of pure elements are known as chemical superconductors. Some allotropes of carbon such as fullerene, nanotubes or diamonds are usually chemical superconductors. Most superconductors made of pure elements are type 1 except niobium, vanadium, silicon and the above mentioned carbon allotropes. The second category of superconductors use alloys as the superconducting material. These alloys include niobium titanium alloys, germanium niobium alloys or niobium nitride as the material. Ceramics, which are often insulators in the normal state, which include cuprates, that means copper oxides, the YbCO family, which are several yttrium, barium, copper oxides, are examples of second type of superconductors. They are the most famous high temperature superconductors also. Iron based superconductors, magnesium diboride, whose critical temperature is 39 Kelvin, being the conventional superconductor with the highest known temperature. Now let us discuss in detail type 1 and type 2 superconductors. First of all, let us see what are type 1 superconductors. Type 1 superconductors are pure metals which exhibit zero resistivity at low temperatures and have the property of excluding magnetic fields from the interior of the superconductor, which is nothing but Meissner effect. The identifying characteristics are zero electrical resistivity below a critical temperature, zero internal magnetic field, that is Meissner effect, and a critical magnetic field above which superconductivity ceases. The superconductivity in type 1 superconductors is well modeled by the BCS theory. Type 1 superconductors are sometimes called soft superconductors. In type 1 superconductors, the transition from superconducting state to normal state in the presence of magnetic field occurs sharply at the critical field value represented by Hc. Some examples for type 1 superconductors include pure elements like aluminum, cadmium, tin and zinc. This figure shows the magnetization curve of type 1 superconductor where the applied magnetic field H is taken along the x-axis. When you apply an external magnetic field H to the specimen, usually magnetic moments will be generated which will be aligned either in the direction of the externally applied field or opposite to it. Since a superconductor is a diamagnet, here the internal magnetization will be equal and opposite to it. Since the superconductor is a diamagnet, the internal magnetization will be usually equal and opposite to the externally applied magnetic field. This internal magnetization is taken along the y-axis, that is M is taken along the y-axis. Here you can see that it's not M, it is minus M that is taken along the y-axis. This is just to indicate that as the external magnetic field increases, that means along the x direction the magnetic field increases, the internal magnetization also increases but in the opposite direction because it's a diamagnet. In other words, on the application of an external magnetic field, an equal magnitude of internal magnetic moments will be generated, but all of them will align in a direction opposite to the external magnetic field. The internal magnetization simply represents the total number of magnetic moments per unit volume. Now you increase the value of externally applied magnetic field gradually, like this. What happens to the internal magnetization? You can see from the graph that the magnetization of the material grows in proportion to the externally applied magnetic field H. Now assume that the external field reaches a value known as the critical magnetic field represented by Hc, this value. At this point, you can see that the internal magnetization abruptly drops to zero, which marks the transition to the normal state from the superconducting state. For magnetic fields less than the critical field, the magnetic field induced in the specimen or in the superconductor is equal and opposite to the external magnetic field, or the specimen is a perfect diamagnet or a superconductor. And for magnetic fields greater than the critical value, the specimen will be in the normal state. As we know, when the specimen is in the normal state, the magnetic field lines will penetrate through the interior of the specimen. This type of superconductors exhibit complete Meissner effect when it is in the superconducting state, which implies that they are diamagnetic in nature. The value of critical magnetic field Hc for type 1 superconductors is always low. Type 1 superconductors have been of limited practical usefulness because of two important reasons. The first reason is the critical magnetic fields are so small and the superconducting state disappears suddenly at that temperature. That means you need to apply very feeble magnetic fields to maintain superconductivity, and it's very difficult to maintain such a low value of external magnetic field for a long time. Second reason, the magnetic field lines can penetrate only the surface layer and the current can only flow in this layer. This implies that the supercurrent generated will be a surface current only. These surface currents shields the internal bulk of the superconductor from the external applied field. As the field expulsion or cancellation does not change with time, the currents producing this effect do not decay with time. This current is known as persistent current or screening current. That's all about type 1 superconductors. Now let us see type 2 superconductors in detail. Superconductors made from alloys are called type 2 superconductors. Besides being mechanically harder than type 1 superconductors, they exhibit much higher critical magnetic fields. Type 2 superconductors such as niobium, titanium are used in the construction of high field superconducting magnets. These superconductors are also known as hard superconductors. This graph shows the internal magnetization versus applied magnetic field curve. As in the previous case, the strength of the externally applied magnetic field H is taken along the x-axis of the graph, and the internal magnetization generated is taken along the y-axis of the graph. Here also the negative value of M, internal magnetization, is taken along the y-axis, implying that the direction of internal magnetization is opposite to that of the external magnetic field. From this figure, it is clear that type 2 superconductors usually exhibit two critical magnetic fields, Hc1 and Hc2. Hc1 is known as the lower critical magnetic field and Hc2 is known as the upper critical magnetic field. For values of the field less than Hc1, that means this region, the material behaves like a perfect diamagnet or as a perfect superconductor, and the external magnetic flux is completely expelled from the interior of the material when it is in this region. So in this region, the entire sample is superconducting, as in the case of type 1 superconductors. Now you increase the external magnetic field from Hc1. You can see that the lower critical field value Hc1, the magnetic field lines begin penetrating the material. Then that means when you increase the magnetic field value from Hc1, the magnetic field lines usually begin to penetrate that specimen. Now you further increase the magnetic field. What will happen to the curve? Instead of having an abrupt drop in magnetization, you can see a gradual drop in internal magnetization until the upper critical field value Hc2 is reached. Here, this dotted line actually represents the internal magnetization curve for type 1 superconductors. What does this gradual drop in magnetization imply? It implies that still the internal magnetization is opposite to the direction of the external field, but its strength gradually decreases. What does it mean? It means that there exists not that much magnetic moment now which oppose the externally applied field. That means some magnetic moments will begin to align in the direction of the external field. So the material experiences a net magnetization instead of zero as given by Meissner effect. In other words, as there is not much resistance to the externally applied magnetic field, some magnetic field lines, that means external magnetic field lines, will begin to penetrate the material now. This will continue until the upper critical magnetic field value Hc2 is reached, where the internal magnetization completely drops to zero. Thus, for applied fields between Hc1 and Hc2, there will be partial penetration of magnetic fields. This means that these superconductors exist in a mixed state of normal and superconducting regions. This figure represents the mixed state. This square actually represents our superconducting specimen. These colored circles represents the normal region within the superconductor. In this region, actually partial penetration of magnetic field lines occur. That means in this colored regions, partial penetration of magnetic field lines occur. That means this region behave as a normal conductor. All these colored regions usually acts as normal conductor. But what about the surrounding region represented by the circle with arrow? This is the region where no magnetic field penetration occurs. And this region still acts as a superconductor, and a supercurrent flows through this region surrounding the normal region. That means these colored regions are act as normal conductors, and a supercurrent flows surrounding that normal region. The arrow represents the direction of current flow. This mixture of normal and superconducting state is actually known as mixed state. So between lower critical field value Hc1 and upper critical field value Hc2, the specimen is in a mixed state. This is sometimes called as vortex state because vortices of superconducting currents surround filaments or cores of normal material. So this is the normal core and a supercurrent flows surrounding that region. The field lines are confined to flux tubes or vortices, as you can see from this figure. In flux tubes, the material will have normal resistivity. That means here it will be having normal resistivity. But at the same time, a supercurrent represented by these circles flows through it. So you can see that only certain integral values of flux lines can pass through each such flux tubes. Only a limited number of flux lines can pass through each of these flux tubes. That means in between Hc1 and Hc2, the material is in a magnetically mixed state, but electrically it is a superconducting state. Now let us check the magnetization curve again of type 2 superconductors. As seen from the curve, after Hc1, which is the lower critical magnetic field value, The magnetization gradually decreases and reaches zero value when the strength of the external magnetic field becomes equal to Hc2. So Hc2 represents the upper critical magnetic field value. That means as the magnetic field is further increased from Hc1, more and more regions of the specimen will change to normal conducting state and more number of magnetic flux lines will begin to penetrate the specimen. Thus the mixed state spreads over the entire region gradually, and if you further increase the magnetic field value, almost the entire specimen will allow magnetic flux lines to pass through it. Thus the mixed state spreads over the entire region gradually, and the specimen will completely change to a normal conductor. That means beyond Hc2 the specimen will completely become or act as a normal conductor, and this occurs at a field value of Hc2, and this is usually known as the upper critical field value. If you further increase the magnetic field, the specimen will completely become a normal conductor. That means there won't be any superconducting regions within that specimen. Thus it is very clear that you can still use the specimen as a superconductor until the upper critical magnetic field value, in contrast to a type 1 superconductor where the specimen behaves as a superconductor up to a very small value of magnetic field Hc. Thus it is clear that up to Hc1, the lower critical magnetic field value, the specimen shows complete Meissner effect, where there is a complete expulsion of magnetic field from the interior of the specimen. No magnetic field lines will be able to penetrate through the specimen up to Hc1. Between Hc1 and Hc2, there exists partial penetration of magnetic field lines, and the specimen will not obey complete Meissner effect in this region. Thus type 2 superconductors does not exhibit complete Meissner effect. Since a supercurrent flows through the specimen up to the upper critical magnetic field value Hc2, which is usually very large, type 2 superconductors are used for most of the practical purposes like in MRI scanners, maglev trains, etc. Also in the case of type 2 superconductors, there is no persistent surface current which hinders the penetration of magnetic field lines into the specimen. That means current flows through the bulk of the specimen itself, not through the surface. Type 1 superconductors are pure metals, whereas type 2 superconductors are alloys. Hence, it is easy to convert type 1 superconductor to type 2 superconductor by adding certain impurities to it. Type 1 superconductor made of lead can be converted to type 2 superconductors by adding sulfur to it.